All right, so we're going to look at problem number 3 here on worksheet number 1. It reads, oil from an uncapped oil well in the ocean is radiating outward in the form of a circular film in the surface of the water. If the radius of the circle is increasing at a rate of 2 meters per second, how fast is the area of the film growing when the radius is 100 meters? I don't know if you remember a few years ago in the Gulf, there was an uncapped oil well and it was spewing oil. It was crazy. And when an uncapped oil well, meaning in the bottom of the ocean, there's this massive release of oil that because oil is less dense than water, comes to the surface. And when it gets to the surface, it starts spreading out, and it's going to spread out in a circle. So that's what's happening here. I'm going to switch over to sharing my piece of paper that I can write on, and we'll draw some diagrams first. We'll lay out the important information and then draw some diagrams. So if you're taking notes with me, that would be good. Let's see. So oil from an uncapped oil well radiating outward in the form of a circular film on the surface of the water. If the radius of the circle is increasing at a rate of 2 meters per second. Okay, so we have a circle with a radius. I'm drawing it like an oval because it's on the surface of the water. I'm trying to have perspective. Radius. The change in radius, dr dt, the change in radius is 2 meters per second. Is equal to 2 meters per second. How fast is the area of the oil film growing when the radius is 100? So how fast the area is growing is going to be dA dt. How fast the area is growing is the question when the radius is equal to 100 meters. All right, so that's the problem we have. And in doing so, it seems like we need to relate area to radius. So that doesn't sound so terrible to relate because, well, area is determined radius. So what's our equation going to be that we're going to work with?
Pi r squared.
Yeah, pi r squared. So area equals pi r squared. All right. And there's no fancy substitution that happens here in this one. We don't want to put this 100 in now. So one of the key mistakes that students make when we start with this is we have to do a substitution. We have to substitute this 100 in for r at some point. But if we substitute it in now, we're substituting in algebra. I don't know if you remember when I stated at the very beginning of class that you've been studying algebra for years, and algebra is the calculation of what happens at a particular point, where calculus is the study of how things change, right? And that's really where we are now. We're talking about rates of change, the rate of change of radius, the rate of change of area with respect to time. If we substitute this 100 in for r now, we're doing algebra. Nothing's changing. We're just going to wind up calculating what the area is at that moment, right? So we don't substitute this moment in time until after we do the calculus, even though that is a moment in time, right? Don't substitute early. Don't substitute too early. However, in some problems, there are going to be some things that we need to substitute before we derive. But in this case, we have area in terms of radius. We're going to take the derivative. So implicit differentiation. Arabella, can you do the implicit differentiation here in terms of t?
You mean just find the derivative of
the equation given?
Yep.
Would it be 2r?
This part's 2r,
Mm-hmm.
well, with pi in it also. So 2 pi r, but we also have to take the derivative of r in terms of t as the chain rule.
So dr dt.
Yep. And then on the other side, what's the derivative of a? Everybody turn off mute for a second.
dA.
dAdt. Okay. All right. So we have our derivative now, and we were given that the radius is changing at 2 meters per second. The radius is changing at 2 meters per second. So now that we've taken the derivative, after we've taken the derivative, we can start to plug in our situation. So dr dt is 2. The radius is 100 at that particular moment, and 2 pi is 2 pi. And dAdt is what we're being asked for. So this one actually set up pretty nicely in that we didn't have a whole lot of fancy algebra to do. And dAdt is going to equal, looks like 400 pi. 400 pi. And that's because it's a range and area that's meters squared per second. So the change in area is 400 pi meters squared per second, about 1,200 square meters every second if the radius is changing at 2 meters per second. All right, I'm going to stop the recording for a minute. And I'll take